Welcome! In this lesson, we will explore the hydrogen bomb, its origin, how it works, and its implications for science and society. Although this is a heavy and serious topic, our goal is educational, to understand the physics, history, and context of this powerful weapon. Let's begin. The term hydrogen bomb refers to a type of nuclear weapon that derives its destructive energy primarily through nuclear fusion, in contrast to the simpler atomic bomb which relies on nuclear fission. Combandis, Encyclopedia Britannica, Sykes. In a thermonuclear bomb, fusion occurs when light atomic nuclei, typically isotopes of hydrogen, such as deuterium and tritium, combine under extreme temperatures and pressures to form heavier nuclei, for example helium. In the process, a small portion of mass is converted into energy, as described by Einstein's famous equation, E = mc2, Encyclopedia Britannica. Because fusion releases much more energy per unit mass than fission, many hydrogen bombs can yield explosively powerful results, often expressed in megaton equivalents of TNT rather than kilotons as with many early atomic bombs. Encyclopedia Britannica. However, it is important to note, a hydrogen bomb does not rely exclusively on fusion. Instead, fusion is triggered by a fission primary stage, making the full device a hybrid of fission plus fusion. Wikipedia. SPAO. The concept of using fusion for explosive purposes was developed in the 1940s, soon after the success of atomic bombs in 1945. Research at the Manhattan Project and related efforts led scientists such as Edward Teller and Teller-Ulam to propose designs for what was called the super weapon. Arms Control Center. The first full-scale thermonuclear test by the United States took place on November 1, 1952, Operation Ivy Mike, in the Pacific at the atoll of Eniwetok Atoll, producing a yield of about 10.4 million tons of TNT, 10.4 megatons, or more. Arms Control Center. Following this, other nuclear weapon states developed their own thermonuclear devices. The rapid escalation of destructive power changed the scale of nuclear deterrence and arms race strategy, which became This history is relevant not just for physics, but for geopolitics, ethics, and international security. Now let's step through how a hydrogen bomb works at a high level, in three major phases. 1. The primary, fission stage. In the first stage, a conventional nuclear fission bomb, using plutonium or uranium, detonates. This produces an immense amount of energy, radiation, and extremely high temperatures and pressures. The device is often configured in an implosion geometry to compress the core to supercriticality. OSDI. This primary explosion creates X-rays and a flood of neutrons, which are directed toward the secondary stage inside the bomb casing. 2. The radiation compression, secondary stage. In the so-called Teller-Ulam configuration, named after Teller and Ulam, the radiation from the primary compresses and heats the secondary stage. This compression helps to raise temperature and pressure high enough to initiate fusion. Wikipedia. Inside the secondary is fusion fuel, typically lithium-6 deuteride. When neutrons produced by the primary hit the lithium, tritium is bred, which then fuses with deuterium under extreme conditions. Atomic archive. In fusion, the light atomic nuclei merge into heavier ones, for example, deuterium plus tritium, helium plus neutron, releasing enormous energy. 3. The tertiary, fission boost and fallout. After fusion begins, high-energy neutrons released may cause surrounding heavy materials, such as uranium-238 in a tamper or casing, to undergo fast fission, further increasing yield and producing large amounts of radioactive fallout. Encyclopedia Britannica. The entire sequence, from primary detonation to heavy neutrons to possible tertiary fission, happens in fractions of a second. The result is a massive release of energy. Blast, heat, radiation, and shockwave. Arms Control Center. Why fusion? Fusion is more efficient per mass than fission. Also, the design allows much larger yields than would be practical with pure fission alone. The key challenge is achieving the temperature and pressure for fusion, which is why the fission trigger is necessary. It's dawan di oper bawan daxer, mi dawan di kordi di infrer. Encyclopedia Britannica. Summary diagram, suggest on screen. Fission bomb, X-rays and neutrons, compress fusion fuel, lithium-6 deuteride, tritium plus deuterium, helium plus neutrons, plus energy, secondary neutron stage, high yield plus, heavy material fission if included. Feel free to show schematic visuals of a two-stage thermonuclear device. The yields of hydrogen bombs can be enormous. While early atomic bombs had yields in the tens of kilotons of TNT, thermonuclear devices can achieve megaton yields, often hundreds or thousands of times greater. Sen sodo budur krababani maatsi, inama, Burns Encyclopedia Britannica. For example, the first U.S. test achieved around 10 megatons. Arms Control Center. What does this mean in terms of destructive effects? The blast wave can destroy buildings and infrastructure at many miles radius. The thermal radiation, flash, can cause widespread fires and cause blindness over tens of miles. Encyclopedia Britannica. Ionizing radiation and fallout pose long-term hazards to living beings and the environment. Because of the larger yield, a hydrogen bomb has far more destructive radius, more intense effects, and more severe long-term consequences than earlier atomic bombs. Truman Library. These facts underscore both the scientific power and ethical gravity of such weapons. Why should we study the hydrogen bomb beyond its physical science? Several reasons. 1. Scientific and technological knowledge. Understanding fusion and fission is central to nuclear physics, energy generation and astrophysics. Our sun uses fusion. 2. Historical context. The advent of thermonuclear weapons changed geopolitical strategy, deterrence, arms race, treaties. 3. Ethical, humanitarian and environmental issues. The existence of weapons of this scale raises questions about war, disarmament, non-proliferation and the effects of radiation on populations and ecosystems. 4. Future applications and risks. While fusion energy holds promise, the fusion in bombs and civilian fusion plants have very different contexts. Also, the potential for proliferation remains a concern. In short, the hydrogen bomb is not just a weapon of war, it is also a teaching point for science, technology, policy and ethics. To summarize, a hydrogen bomb uses a two-stage or more process. Fission triggers fusion, and optionally additional fission of heavy material boosts the yield. Fusion of light isotopes, deuterium, tritium, under extreme conditions is central to the energy release. Yields are vastly greater than pure fission weapons, making the destructive potential enormous. The development of thermonuclear weapons marked a major turning point in both science and geopolitics. As you reflect on this topic, remember, the same scientific principles that enable understanding of the cosmos and energy production also underpin some of the most destructive weapons humans have ever made. Our learning is meant to empower responsible knowledge, not glorify destruction. Thank you for watching. Please feel free to pause, rewind, or replay segments to clarify any point. If you have questions or want to dive deeper into fusion physics, weapon design, or global policy implications, let me know.